Hello, this is the first of two complex number videos on the Argand diagram. This session introduces the Argand diagram and shows how to represent addition and subtraction of complex numbers on it. We are used to using two-dimensional graphs to represent x and y coordinates where both axes are real. In forming the Argand diagram, we start with the real axis and then consider geometrically what happens when 1 is multiplied by -1. Multiplying by -1 produces a 180 degrees rotation about the origin. We can remember from previous sessions on complex numbers that we've defined the square root of -1 as I. Let us now consider what multiplying by I, or the square root of -1, do. It might be a 90-degree rotation. If multiplying by I produces a 90-degree rotation about the origin, we now in effect have a real axis and an imaginary axis in a 2D complex plane. This is called an Argand diagram. Let us consider a complex number z1 equals 3 plus 4i. We can represent this by a point in the Argand diagram, which will have coordinates 3, 4, where we can see that the 3 is the real part and the 4 the imaginary coefficient. So whilst we can represent that complex number by coordinates 3, 4, i.e. a point in the Argand diagram, we can also think of it as a line joining the point to the origin, rather like a vector. In previous sessions, we looked at the idea of complex conjugates as being the roots of quadratic equations. Consider the complex number z equals 4 plus I, then the complex conjugate would be denoted by z star and equal to 4 minus I. Here they are plotted on the Argand diagram. What do we notice about their relative positions on the Argand diagram? And can we generalize this? Once you've tried some examples for yourselves, you will probably realize that complex conjugate pairs are reflected in the real axis. In session 1.2, we looked at adding complex numbers algebraically. If we consider the addition of z1 and z2, algebraically that would give us 2 plus 5i plus 5 plus I, leading to 7 plus 6i. If we look at these two complex numbers on the Argand diagram, we can see that indeed z1 is at the 2 plus 5i point coordinate, and that z2 is at the 5 plus I. We can also represent z1 plus z2 equals 7 plus 6i on the diagram, as shown here by the blue line. Given that we can treat complex numbers like vectors on the Argand diagram, you may be able to spot how else we could reach 7 plus 6i using the vectors z1 and z2. If we first travel along z1 and then in effect travel along z2, we will reach 7 plus 6i. If we consider subtracting complex numbers, for example this z1 minus z2, then algebraically we know that this is easily worked out. And will give us 5 plus I. We can also show this on the Argand diagram. So starting with z2, if we then subtract z1, indicated by the direction of the arrow on the vector, then you can see that we will end up at the coordinate 5, 1. The answer or in other words z2 minus z1 equal to 5 plus I is here therefore shown geometrically by this blue line. I would recommend that you have a play around with complex numbers on the Argand diagram, practicing addition and subtraction on this GeoGebra website. You can either cut and paste this into your normal browser, or you can get to it through the integral resources. In the next session, 2.2, we will look at representing rotation and multiplication by eye on Argand diagrams.